In the 1980s, scientists made a startling discovery. A massive hole in our planet's protective ozone layer was growing over Antarctica. The culprit? Chemicals called CFCs found in everyday products like hairspray and refrigerators. The prognosis was dire: increased skin cancer, crop damage, ecosystem collapse. But now, nearly 4 decades later, that same ozone hole is healing. The Montreal Protocol, perhaps the most successful international environmental agreement in history, has led to a 99% reduction in the ozone-depleting substances.
Chlorofluorocarbons since the year 2010 have been fully controlled for consumption and production.
And according to MIT's recent research, the healing is directly linked to humanity's deliberate choices and actions. In a world that often feels paralyzed by environmental crisis, this Earth Day we are going off the radar and celebrating a triumph of human determination and cooperation. This isn't just a scientific victory, it's proof that when we choose to act together, we can heal our planet.
The Montreal Protocol has worked. Nations can get together and take action on global problems.
I'm meteorologist Emily Gracie, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the ocean, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do.
Craving your next action-packed adventure? Audible delivers thrills of every kind on your command, like Project Hail Mary by Andy Weir, where a lone astronaut must save humanity from extinction, narrated with stunning intensity by Ray Porter. From electrifying suspense and daring quest to spine-tingling horror and romance in far-off realms, unleash your adventurous side with gripping titles that'll keep you guessing. Discover exclusive Audible originals, hotly anticipated new releases, and must-listen bestsellers that hook you from the first minute. Because Audible knows there's no greater thrill than the one that speaks to you. Discover what lies beyond the edge of your seat. Start your free 30-day trial at audible.com/WonderyUS. That's audible.com/WonderyUS.
Welcome to Off the Radar. I'm your host, Emily Gracie. On this Earth Day, we are doing something a little different. Instead of focusing on the environmental challenges we face, we're highlighting an extraordinary success story: the recovery of Earth's ozone layer. The recent MIT paper confirms what many scientists have long hoped. Our collective action to phase out chlorofluorocarbons, or CFCs, is working. The ozone layer is healing. It's a powerful reminder that humans can be a force for planetary good, not just harm. Today, I'm joined by Dr. Paul Newman, a senior atmospheric scientist with the University of Maryland Baltimore. Dr. Newman is semi-retired now, but has been at the forefront of ozone research for decades, serving as chief scientist for Earth Sciences at NASA's Goddard Space Flight Center. He was also the co-chair of the scientific assessment panel to the Montreal Protocol, playing an essential role in keeping CFCs out of the atmosphere. Today, we'll explore the history of the ozone crisis, that groundbreaking international agreement known as the Montreal Protocol, and what this environmental success story may teach us about tackling climate change. Dr. Paul Newman, thanks so much for talking to me today about the ozone hole. I am a child of the 80s and 90s, so this was our big problem. I grew up thinking about this and being told about this in school a lot, the same way that children today are being talked to about climate change. Mm-hmm. So can we go way back to like the 70s and 80s and tell me what the problem was with the ozone hole and how that happened?
Well, in 1974, a couple of scientists, Mario Molina and Sherry Rowland, published a paper suggesting that chlorofluorocarbons, CFCs, we used to use them in air conditioners and hairsprays, they had very long lifetimes, very stable molecules, so great chemicals for all sorts of things, but that these chlorofluorocarbons could get into the stratosphere and destroy ozone. Now, the reason that's of concern is because ozone screens solar ultraviolet radiation, and UV, all about ultraviolet radiation or UV, can damage biological molecules, carbohydrates, proteins, most particularly for humans, DNA, and also for plants and animals. These CFCs were an existential threat. That is, the CFCs could deplete the ozone layer, and with no ozone layer, life on the Earth's surface could not exist. So this was a serious problem. Now, in 1974, it was a hypothesis. But with years of work, it was shown that, in fact, it was true that CFCs could deplete ozone. It was shown in labs. There were laboratory studies. There were modeling studies. But then we found out in 1985 that there was this huge downward trend of ozone over Antarctica, well beyond what could be considered observational air. And so we knew something odd was going on over Antarctica. And it turned out that it was a very special kind of chemistry that we hadn't thought, people had not really thought that this could happen in the atmosphere. That is, you could get chemicals that as gases would not react, but they could react on the surfaces of a particle. And so we found that two relatively benign gases, HCl and chlorine nitrate, could react on the surface of these very tenuous clouds over Antarctica. And they could release chlorine into a form that could catalytically destroy ozone. The catalytic process is something where a chlorine atom will destroy an ozone molecule and then regenerate itself. That was the discovery of the ozone hole was in 1985. And there was a whole bunch. So remember, 1974 is when it started. 1985 is where we discovered that there was very large ozone depletion over Antarctica. And by 1987, we had pretty much solved the problem. There were a number of theories in 1985, but turned out that the theory that said it was the chlorofluorocarbons that were causing the ozone hole was shown to be correct. We flew NASA's ER-2 aircraft. It's the civilian version of the famous U-2 spy plane. It was flown over Antarctica, up at 20 kilometers, so 70,000 feet. And it flew right into the ozone hole a number of times. It was able to show that ozone was going down, and that where ozone was going down, chlorine levels were really high. And so we found the ozone hole, and we found that it was due to man-made chemicals.
Okay, so what does a world with an ozone hole look like? If nothing had changed, you said DNA is impacted. What does that look like?
Well, first of all, if chlorine had kept going up, and we did a study here at Goddard, gentleman here, Dr. Luc Oman and myself did a study where we looked at what would happen if chlorine CFCs had kept increasing 3% per year. Now, CFCs back in the 1970s were going up at about 9% per year. Everybody was buying refrigerators and air conditioners. Cars had air conditioners that were using CFCs and so forth. So CFCs were going up pretty quick. Everybody was using it in hairsprays and deodorant. So
I remember the 80s, yeah.
And so we did a study where we put it into a model. This is a very complex three-dimensional model that we ran in time. And so we kept increasing CFCs. And so by the year 2065, we had destroyed 2/3 of the ozone layer. Now, for people, what did that mean? Well, it typically, a guy like me I'll get a visible sunburn. If I'm out in the sun in the middle of the day, I'll get a visible sunburn in 15 to 20 minutes. And by the year 2065, if we've done nothing, CFCs had kept going up 3% per year, ozone would have decreased by 2/3. That meant that I would have gotten a sunburn in something like 3 to 5 minutes. Now that's for people. Now also, because you're damaging DNA, there have been more skin cancer, cataracts, your eyes are damaged, photoaging, so degradation of materials. Back in the day, our dashboards on cars would crack. They would corrode and crack because of UV radiation. More importantly, crop yields would go way down. And that's where things really get tricky, because if you can't grow enough crops to feed the people, there are serious outcomes to that. People, food decreases, people riot, people starve. It would have been a pretty rotten world to live in.
Okay, so this is scary enough for people to come together, and along comes the Montreal Protocol. Can you explain that to me and how that came along?
Yeah. So after the 1974 study, people began to think hard about, well, maybe we should slow down the use of chlorofluorocarbons. And so there began to become international agreements. Countries were starting to get together to negotiate what to do about CFCs or what to think about CFCs. In 1985, the Vienna Convention was signed, an agreement amongst nations that ozone depletion was a problem and we needed to do scientific investigations of ozone depletion. The United States, the U.S. Senate ratified the Vienna Convention, signed by Ronald Reagan. And so that committed the United States to maintain an ozone research program, of which NASA is obligated to be part of. And there's a Clean Air Act that actually mandates NASA and NOAA to make reports to Congress every few years. So that was a great agreement. It agreed that there's a problem and we needed to do scientific investigations of that problem. Along in 1987, a protocol to the Vienna Convention was drafted. That was the Montreal Protocol of 1987. Now, the Montreal Protocol initially just slowed down. It just capped production. Didn't stop the production of chlorofluorocarbons. It just slowed things down. Like I said, people were being cautious in the 70s and 80s. This is an identified problem. The scientists are saying that it's more than likely real. We've done calculations. It shows all these things. The ozone hole had popped up, and maybe it was caused by chlorofluorocarbons. In the time that they were negotiating these things, they didn't know. But they thought, well, let's pump the brakes a little bit. We're going pretty fast on CFCs. Let's pump the brakes and slow things down. Okay? Let's not turn around yet, but let's at least slow down. And so they did. And the United States ratified that in the U.S. Senate, and it was signed by Ronald Reagan in 1988. So the U.S. is a signatory to this agreement. Now, over the years, the Montreal Protocol has had amendments that have strengthened it. And so chlorofluorocarbons, since the year 2010, have been fully controlled for consumption and production. Now, there have been a few violations over the years, but since 2010, we can see that the consumption and production has stopped. And since about the 1990s, mid-1990s, CFCs were going up and up. And in the mid-1990s, they kind of topped out, and now they've been slowly going down. But as I mentioned, CFCs are very stable molecules. Their lifetimes are on the order of 50 to 100 years or more, depends on the particular chlorofluorocarbon. So they're slowly going down because of their long lifetimes. So we produced a lot of them. They went up pretty fast, and now they're on this gentle downslope. For the Antarctic ozone hole, we predict that it's sometimes in the 2060s, 2070s, that the ozone hole will go back to the 1980 level, a more natural level. So the projections are all positive as long as nations continue to abide by the Montreal Protocol.
Okay, and then we had this study that came out from MIT talking about fingerprinting and how it can be directly correlated to this change. Can you explain what fingerprinting is and how that study worked?
So this goes back to models. We've been looking at the ozone hole for many years now. We have satellite measurements that go back to the early 1970s. We have ground measurements that go back to the 1950s. So we have a lot of observations of ozone, but it's the atmosphere. It wobbles around. Every year is a little bit different, and so chlorofluorocarbons are slowly going down. Now it takes about 5 years or so. If we make a change down here in the lower atmosphere, it takes about 5 years for that change of chlorofluorocarbons to appear over Antarctica. So there's a delay. So so we've been looking at ozone over Antarctica since the early 2000s. We had very, very large ozone hole in the first decade of the 2000s. And things have slowly been coming down. So we see that in the observations. And so the next question is, well, okay, is it a result of the Montreal Protocol? And this is where our theory and models come in. Now, models represent our collective knowledge. You know, how much CO2 is in the atmosphere, how much methane, how much nitrous oxide, how much of the CFCs and hydrochlorofluorocarbons, all these other gases collectively, if you put them into a model and you run the model, and these models produce, weather and everything. They're full coupled chemistry, three-dimensional coupled chemistry, climate models. They produce, the climate of Antarctica and the stratosphere. And so if we change, because the CFCs are changing, they're going down, do we see a comparable change in ozone? So these models also vary year to year to year, just like the real atmosphere does. And so what they did is they ran the model a number of times. They come up with what we call an ensemble of simulations. So, every year it's going to be a little different. You really don't do forecasts, but you can come up with a range of what you think the atmosphere will do in, say, the year 2030 or 2040. And you can simulate it for, different conditions for the 2020s now. And so that's what they did. They took an ensemble of models and they looked at what is the fingerprint of decreasing ozone in that model. And then they compared it to observations. Okay, do they give us the same kind of trend? And the answer is they do. You get basically the same sort of appearance of ozone recovery in the model as you do in the observations. The model, the fingerprint is the matching of the trend pattern.
So the study shows that we're headed in the right direction. We're doing something right. We're fixing a problem we created in the first place, but we're fixing an issue.
This study actually shows that you can directly tie the chlorine. Remember, the model is our full understanding of the transport dynamics, chemistry, radiation. That shows that what we expect to be happening is happening. Now, it's not quite the same magnitude, but the picture is exactly the same. And that's great news. But, in a couple of years, we may not have the observations to continue to see this change in the next few years.
Okay, so important that we stay on that. But the elephant in the room, I think, also is climate change, because we know CO2 is causing this issue, and we've known for a while. So why is there no situation like the Montreal Protocol where we are making that change?
Simply, it's a much bigger issue for carbon dioxide than it was for chlorofluorocarbons. Chlorofluorocarbons, they had replacements. All of our car conditioners now have new carrier gases. Our home air conditioners have new carrier gases and so forth. We no longer use CFCs and hairsprays and deodorants and so forth. Those have been replaced. How do you replace gasoline-fueled cars, fossil fuels, coal plants? It's a much bigger, harder issue to deal with. And so that's the primary reason. I think there is hope, though. It is my political perspective. I take my scientist hat off. The Montreal Protocol has worked. Every nation on the earth has signed the Montreal Protocol. That's good news. Nations can get together and take action on global problems. It hasn't happened with fossil fuels. It hasn't happened yet. I hope that we don't have larger, greater environmental problems that will drive that. I hope we can act before that happens. But I think there's hope that we can get there because we have the example of the Montreal Protocol.
How do we get there?
Let's keep observing things. It's all about the data. If you don't have data, you can't say anything. Problems can rise up and ambush you. You want satellites to monitor the Atlantic to make sure a hurricane suddenly doesn't appear and wipe out a city because we were watching. We need observations. And the government is the only institution that's going to pay a lot of attention to the ozone layer. And so let's hope we continue to make those measurements so that we can inform policymakers and the public about how their ozone layer is changing, because it is fundamental to life on the Earth's surface.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes publish every Tuesday. You can also follow us on Instagram. Just look for Off the Radar Podcast. Thank you to Dr. Paul Newman for all he has done for the planet and for sharing his expertise today. Thanks to the National Weather Desk and Sinclair Broadcast Group for their ongoing support of the podcast, as well as my associate producer, Brian Petras, for his help with today's episode. I'm meteorologist Emily Gracie. Make it a great day.